True or false? The midpoint of a hypotenuse of a right triangle is equidistant from the three vertices. Take a second to think about it, and then we're going to hop into it. Okay, so first things first, we're probably going to want to draw a quick diagram of a right angle triangle. And it doesn't mention anything about this right angle triangle. We're not being told whether it is isosceles or not, or what the angles are. So I'm just going to start off by drawing a generalized right triangle. So one that does not look specifically like it is anything in particular. Okay, so what we can see here is we have the base of our triangle, which we can label as A. We have the height, which we can label as B. We've got the hypotenuse, which we can label as C, as we do for the Pythagorean theorem. Now we know we have a right angle in this bottom corner. And what we're talking about here is the midpoint of the hypotenuse. So if I can just put that midpoint right around here, that's the midpoint of our hypotenuse. So we're trying to see if it's true that the midpoint is equidistant from the three vertices. So what we'll do is we'll maybe just draw a few arrows that show what those distances are. That's one. This is the second distance from that corner. Vertices just mean corners. And this is the third. Now, what we're trying to show, if this is true, is that this is the same thing as this is the same thing as this. It's not immediately obvious that it's true, although it does kind of look, if you do draw the lines, it feels like it suggests that the two triangles that we've split the right triangle into are actually isosceles. So it kind of looks like triangle 1 here is isosceles with an obtuse angle here. And that triangle 2 here is isosceles with an acute angle here. And that obtuse and acute angle add up to 180 because this side C is a straight line, and that would form a flat angle. Okay, just having fun here with the triangle now. Let's take that away for a second. So it might get a little complicated if we try and do this using like a sine law or a cosine law, because we don't really have any angles. But what we might be able to do is apply our knowledge of analytic geometry and almost picture this on a plane, right? We're talking about distances between vertices, between points in space. So we may as well plot this onto a graph and see if we can get any help from our good friend analytic geometry. So let's actually imagine that this right angle triangle is just sitting perfectly at the corner of the Cartesian plane with the right angle at the origin, like so. This would be our x-axis, and this would be our y-axis up here. And if we do that, we could start to label coordinates for each of the points of interest. We have our good friend, the origin here at 0, 0. We've also got this coordinate here at the end of the bottom of the triangle, which is our coordinate a units away along x. So a units away along x should be the x coordinate of a, and we're still on the x-axis, so the y would be 0. And similarly, we can look at the symmetry here. This point on top is going to be on the y-axis. And so the x value will be 0, and the y value is going to be b units away from the origin. So we're going up by b units. Last but not least, the most important point, I think, for the whole problem is what we have here alongside C, which is that midpoint. Now, we know that a midpoint along a line should be halfway towards A and halfway towards this height B. That's how we find the midpoint. And so the coordinate of this midpoint should be half of A along X and then half of B along Y. And that would be our coordinate there. Maybe I'll make this a bit nicer for you. We'll go like this: A over 2 and B over 2. Okay. With this in mind, we just need to apply the distance formula 3 times. So that's what we're going to do. The plan is to apply distance formula 3 times. And if all of the distances are the same, then we've proven that this is absolutely true. That it is true that the midpoint of a hypotenuse of a right angle triangle is equidistant from the 3 vertices. So I'll just demonstrate one of these for you to start off. So the distance formula will go d for distance The distance formula is going to be the square root of, and this comes from the Pythagorean theorem. I'll maybe do a different video on that, although there are plenty out there, I'm sure, already. What we're looking at here is we're going to take the square of the distance between two x values. And then we're going to add that to the square of the distance between two y values. And take the square root of that. And so what we can do is we can take any two coordinates here that are along these red arrows. So we can take this coordinate and this coordinate, find that distance from the midpoint to the coordinate a0. We could also take the distance from the midpoint to the origin and also from the midpoint to this point here. And if they're all the same, then we're good to go. Let's try maybe the simplest one here, which is from the midpoint to the origin. So let's do that now. Midpoint to origin. Okay, so here we're going to have that the distance is square root of, okay, so the first x value is going to be a/2. And the origin is just 0, 0. So we're going to subtract 0 and square that. And we'll add this to, well, what's the y value? b/2. We'll subtract 0 again from the origin and square it. And so the distance is going to be the square root of a/2 minus 0, which is just a/2 squared, plus b/2 minus 0, which is just b/2, and we'll square that again. So the distance is the square root of a squared over 4 plus b squared over 4 if we just distribute the 2's into those brackets using exponent laws. And popping to the left here, what we can do is we can say the distance is equal to the square root of, since they have a common denominator here, we'll just go a squared plus b squared over 4. And we have this factor of a quarter now inside of our square root, which if we pull out of the square root will just become 1/2. So d is going to be equal to 1/2, again, because we're pulling out the factor of a quarter out of the square root, and then square root of a squared plus b squared. Interesting. Now, this is very, very interesting because right off the bat, well, this is beautiful. Right off the bat, though, we can see that that was this length here, which we want to be equal to the other two lengths. The other two lengths, though, lie along the hypotenuse, and they are exactly half of the hypotenuse, which means they should be exactly 1/2 of C. But follow me here to the next page, and we'll come back. C is equal to, or rather C squared is equal to a squared plus b squared. This is our good friend, the Pythagorean theorem, or Pythag for short. So if c squared is equal to a squared plus b squared, then rooting both sides, we get c equals the square root of a squared plus b squared. Uh-oh, do you see it? If c is square root of a squared plus b squared, let's do a quick replacement on the previous page. Whoop. 1/2 of c, well, that's got to be 1/2 of root a squared plus b squared. 1/2 c is 1/2 root a squared plus b squared, based on the definition of the relationship between a, b, and c in a right angle triangle through the Pythagorean theorem. So that means each of the halves of the hypotenuse will be 1/2 of the square root of a squared plus b squared, which is exactly what this line is here. And we're done. It is definitely true that the midpoint of the hypotenuse of a right angle triangle, any right angle triangle here, because we kept it general with a and b and c, that it's going to be equidistant from the 3 vertices. And that's all. So this is a great use of analytic geometry here for us. And I hope that you found this helpful. I'll see you in the next video.